All right, hello everyone. Today I'm going to be teaching you guys how to solve LeetCode 797, all paths from source to target. So we're given a directed acyclic graph with n nodes labeled from 0 to n minus 1, and we want to find all possible paths from 0 to node n minus 1 and return them in any order. The graph is given as follows. All right, I quickly copied over the first example here. As you can see, the graph is given to us as a 2D array, and we can actually look at this like an adjacency list. If you don't know how to read one, that's no problem. I'll show you right now. We can think about each of the indices in this 2D array as a node. So in this case, this would be node 0. And the values inside the list represent its neighbors, or whatever nodes it has directed edges to. So in this case, node 0 connects to 1 and 2. Node 1 connects to 3. Node 2 connects to 3 as well. And node 3 doesn't connect to anything because there's no directed edge coming out from node 3. All right, so our goal is to find all paths starting from 0 to n minus 1, right? So there's a total number of 4 nodes, and we want to get to n minus 1, so 4 minus 1 is 3. So our goal is 3. And we're going to just use a simple DFS, and it's going to have 2 parameters. One is the current node we're at, and next is the path, because we need some way to store all the nodes in the current traversal. So let's start off. First, we start off with node 0, because all paths have to start from node 0, and our path has node 0. Next, we check node 0 inside of our graph to see what are its neighbors. We could either go to node 1 or 2. Let's go to node 1 first. All right, so we're here. Now, our current node is 1, and our path will add 1. We check node 1 in our graph and we say, hey, node 1 connect to node 3. So we travel to node 3. We add that to our path. So node 3. And we see, hey, well, the current node is 3 and our goal is 3. So that means we've found a correct or valid path. So we want to save that somewhere. So let's say we saved it down here. So we have 0, 1, 3. Now, since there's no more options, 3 has no neighbors. We've explored all the neighbors of 1. We have to backtrack all the way back to our last option where we had multiple options. So in this case, that would be 0, because 0, we've explored its first neighbor, but not its second neighbor. And since we backtracked, then that means our current path would only have 0, and we'd be at node 0. And we've already explored node 1, so now we have to explore the second neighbor of 2. And I'm going to highlight this in a different color, green. So we go to node 2. And just to show we're currently at node 2, we add that to our path. We check node 2 inside of our graph. And we see, hey, node 2 has a neighbor or a direct edge to node 3. And it's its only directed edge, so we have no option but to go there. We travel to node 3. We add this onto our path, so we're at node 3, and our current node is 3. 3 is our goal, so we save that to our path, so 0, 2, 3. And we're done, because we've traversed the entire graph looking at all possible paths from 0 to n minus 1. All right, and as for the time complexity, it would be big O of 2 to the n minus 2. And this is the time complexity for the worst case. In this case, this graph is quite sparse, but in a complete connected directed acyclic graph, there'd be many more edges, making this graph much more dense, and there being much more, or many more possible ways to get from 0 to n minus 1. And we do n minus 2 here, where n stands for the total number of nodes, and minus 2 because 2 of the nodes actually don't change in the path. All paths have to start with 0 and end with n minus 1. Only the intermediate nodes would be interchanged, right? And as for the space complexity, it would be big O of n times 2 to the n minus 2, where 2 to the n minus 2 is the total number of paths, and n is the recursion stack. All right, so now let's get into solving this question. First, I like to create a variable called res. Res is just going to hold all the paths that we come across, right? Next, we need a goal. So I'm going to say goal equals n minus 1. So in this case, it would be n would be the length of the graph minus 1. And now we need to have a DFS function. So we define a function, DFS, and it takes a node and a path. And since it's a recursive function, first we have to take care of the base case. And it's if node equals goal, in this case n-1, then what do we want to do? We want to append the path to res. So res.append path, and make sure it's a copy so we don't modify it as the DFS call continues, and return, right? Now we go into the recursive case. We want to explore all neighbors of the current node. So we'd say for nay in graph, and to know all of its neighbors, we say graph at index, whatever the current node is, and we call DFS on the neighbor. And as for the path, we would have the current path plus the neighbor that we're currently traversing to, so nay. There we go. And this is pretty much the entire solution. All we have to do now is call the DFS function. So DFS starting at node 0, and we have a path with 0. And now we just return res. All right, so let's try it out and see how it goes. And there we go. We passed, and it's pretty efficient. So if you learned something new or have any questions, just comment down below. Peace.